Welcome back to the lecture. We will continue the induction motor performance. We have discussed so far about the equivalent circuit, how to convert the rotor to the stator, then how to compute the power, what is the power balance, how much power is crossing the air gap and how much power is getting lost because of the eddy current and copper losses of stator and rotor. Now, we will move on. So, we will again see that we have to use how to do the derivation for torque and speed once you get the equivalent circuit, because it is a complicated circuit. So, we can have three different ways to do it. So, one of the ways is by Thevenin's equivalent. So, what is the Thevenin's equivalent circuit? You remember Thevenin's theorem. If there is a two-port network, if there is a two-port network. Two-port means there are two ports, you can see here like this. So, electrical network, if there is a electrical network and there are multiple ports, out of which if there is there are some sources here like this, you can see, and there is a load connected. So, you can replace this whole thing like a voltage behind an equivalent impedance. This is the basics of Thevenin's theorem. So, we are referring to Fitzgerald and Kingsley. This is the book we are referring to. So, in this book you can see this is the electrical equivalent circuit and we can have this. So, same thing we can do for induction motors as well. So, we can replace the whole equivalent network. So, the whole thing, this whole network can be replaced by this equivalent circuit, one voltage and one equivalent. So, how it is done? So, if you can apply, so terminals A is chosen across rotor branch. So, this is the rotor branch A and B, this is the terminal, you can see. So, you can say that this is the whole thing. The magnetizing branch has been taken out. We have taken this magnetizing branch out and this magnetizing branch is merged with this equivalent circuit. So, you can see this is the original circuit. This is the we have neglected the resistive branch, the eddy current loss we have neglected, because with RE, the eddy current branch, eddy current loss component. So, eddy current loss we have neglected and we have replaced it by a constant power loss P. So, this will not create a lot of errors because this resistance is very high. So, you have taken just this one. So, this whole thing AB, across AB we can replace by an equivalent circuit from here. So, this whole thing can be equivalent circuit like this, you can see here. So, it is V equivalent. So, this is what is done. You can see this whole thing is converted into equivalent circuit, as you can see here. Okay, so, this is the Thevenin's equivalent. So, both circuits are same. So, once it is what will be the equivalent circuit? So, to do that you first open out AB, this branch is opened out. If you open out, so in the Thevenin's equivalent circuit what was happening? That means you first get the open circuit voltage. In Thevenin's equivalent, step 1 is get the V open circuit voltage across the load. So, this is the load. So, this is the load, you can see, this is the load. So, I open it and I found out the open circuit voltage V open. This V open is same as V equal because there is no resistance here. Then I will find out the setting the voltage, I find out the equivalent impedance. Okay, so, I can find that. So, this open circuit is found out by this method, this is V equivalent is equal to, this is open. So, this plot is open, this is not there. So, no current here. So, equal to JXM divided by R1 plus this is just voltage divider, V1 by the total impedance of this into this. So, this is the open circuit voltage. So, this is V1Q. Okay. So, you can also approximate by neglecting the stator resistance, it will not create much errors. Then you find out the equivalent impedance by looking from this terminal. So, you sort it out. So, the equivalent impedance will be, these two will be parallel. So, you can see R1 plus Jx1 in parallel with Jxm. So, you do the parallel thing, this multiplied by this divided by this. So, this is the equivalent impedance. So, this is neglected, as I said, without loss of much of the approximation. So, once you do the equivalent circuit approximation, this whole thing becomes very simple. So, we can do the simplified torque, you can find out the I2. Once you find out the I2, you can find out the resistance. So, you can do everything on the rotor circuit side, because that is what it makes important here. So, now the mechanical power will be how much? This is Q is equal to 3 here. So, this is the total mechanical torque. See, total power. So, total power output by speed, mechanical speed omega r in radian per second. Remember, torque in Newton meter is equal to total mechanical power in watt divided by speed omega r radian per second. And what is omega r? Omega r is equal to starter speed. So, the synchronous speed into slip 1 minus s, because the omega r plus omega slip is equal to the starter synchronous speed, mechanical speed. So, which is equal to pole pair by 2 into electrical speed. Okay. As I said last time, mechanical speed, mechanical speed Wm is equal to the electrical speed by P by 2. Alright, the number of pole pairs. If the P is equal to 2, then it is equal to same, but if P is equal to 4, it will be half of the electrical speed. And if you, this is synchronous speed, then if you multiply 1 minus s, so that becomes the actual rotor speed in radian per second. So, your power loss is how much? Power loss is I2 square into 3 into 1 minus s into R2 by s. This you have done earlier, this you have done already, you see, here you did. This is the power, mechanical power loss, you can see, this you have already done. Mechanical power you have done already. So, this is the power mechanical. Air gap power was how much? 3 I2 square into R2 by s. This minus 3 I2 square R2 by s is the rotor copper loss. So, that is equal to this power. So, this power divided by speed omega r, which is omega e into 1 minus s by P by 2. If you add that, this 1 minus s cancels out, P by 2. So, this P by 2 comes up. So, this becomes P by 2 poles by 2 omega e into 3 I square. So, this is the mechanical. So, you see, mechanical power is proportional to the air gap power. Torque, sorry, mechanical torque is proportional to the air gap torque divided by the, of course, the speed. So, there is, it's a very beautiful expression. So, you can find out I2 from this. This is I2. So, total I2 can be found out by dividing this voltage into by this impedance. So, this is the impedance, I2 can be found out, you see. You can do this too, Z1eq plus R2, so you can do. So, if you do everything together, so this becomes this becomes 3. So, I2 once you find from that, you know, I2 square becomes this, R1q plus R2, X1q plus X2, then plus R2. So, this all these things come in R1q plus R2 by s whole square, this is the impedance square, Z X1q plus 2 square, this is the torque. So, this is the expression of a torque. So, this torque is dependent on a slip in a non-linear way, not in a linear way. So, this is very non-linear equation. If you see s is equal to 1, there will be torque. When s is equal to 0, torque will be 0. You can see by doing some L'Hospital's rule, us is s square here. So, s square goes up. So, s square cancel s. So, only s is multiplied. So, you will see when torque is equal to, when s is equal to 0, torque will become 0. T mechanical will be 0. Because there will be s square here downstairs, down. This s square goes up. So, if you multiply s square, is cancelled out. So, there will be an s torque. So, which will become 0. So, when s is equal to 1 something, and torque will also achieve a maximum value. So, that is, you can see this is how torque varies. This is the torque speed characteristics, and this is power, mechanical power, this is torque. So, when the s is equal to 1, from this expression s is equal to 1, you will find some starting torque. Okay. Then when s becomes 0, torque becomes 0. When torque becomes 0, what happens to power? Power is 0. Here power also will be 0 because speed is 0. Torque into speed is the power. So, this is the power equation, this is the torque curve. So, torque has a maximum value, it is called pull out torque, because beyond that the motor will stop. This is called pull out, that means motor will stop. If you apply load torque, this is the load torque. If you have a load torque like this, so the motor will start. This is load torque. The motor will start because there is a torque here. So, it will pick up and it will operate here. So, but if the load torque, if we keep on increasing, what will happen? Keep on increasing the load torque, if it is beyond that, it will pull out. That means the motor will stall. So, this is the point where there is maximum torque and the slip corresponding to the maximum torque is maximum torque and slip corresponding to the maximum power is max P. So, this curve I have taken from this book. So, this is the power torque characteristic or slip torque characteristic of the motor. Alright. So, once again I will just recapitulate. So, I can do a equivalent circuit. So, this equivalent circuit coming from this circuit, I have neglected the, so I have seen from this side by using Thevenin's theorem. So, I can see the parallel of these two is the impedance and the open circuit is by this rule. So, if I neglect magnetizing, then this is not a problem, but magnetizing cannot be neglected. The magnetizing reactance Xm is small here compared to transformers. Why? Because of air gap. Small in the sense compared to with respect to an equivalent transformer. Why? Because of the air gap. So, therefore, magnetizing current is higher here. Remember this, because Xm is proportional to what? The Lm. Lm is related compared to what? Number of turns square by reluctance. This is N square by reluctance proportional, or N1 Ns into Nr by reluctance. The starter and rotor turn multiply by reluctance. So, reluctance is small because of the air gap. Reluctance is large. If the reluctance is large because of air gap, because it is proportional air gap and permeability of air gap is very low. So, therefore, the reluctance is more, therefore, Xm is low. If Xm is low, what will happen? The current here will be more, though it is more than this I1, I2. So, here in case of transformers, the magnetizing current percentage of full load current is about 2 to 3%, full load current in case of transformers. But for motors, induction motors, equivalent type, Im is about 30 to 40% or more than that of the full load current, even sometimes 50%. So, therefore, since this branch cannot be neglected, you can move this branch here, but again you will commit lot of errors. So, that is why better to analyze Thevenin's equivalent, but if there is no option, you go for that. So, that is how we got then we calculate the current. From the current we found out the power to the rotor, gap power. So, gap power is proportional to this is the gap power, we did it earlier. Then gap power minus the rotor losses, the mechanical power, then divided by the rotational speed, which is equal to electrical speed, synchronous speed by number of pole pairs by 2, omega E by P by 2 into 1 minus S is the rotational speed. If you divide 1 minus cancels, so this is the equation. And then finally, you put I2 is derived from this analysis. Once you put I2, this is the expression, and from this expression I can have a understanding that what happens to the torque slip characteristic. When slip is equal to 1, torque is there, but when slip is equal to 0, that means at full load speed. So, this is omega R increasing, that means this speed increasing, omega. So, the rotor speed basically. So, it is increasing omega R, you can say. When the omega R increases, slip falls down. So, this is how the power and torque is going to behave. So, this is, I think we have done really well till now by understanding this. So, this is what, when there are 3 regions, what happens if the slip becomes more than less than 0, negative. That happens when the rotor speed is more than the supply frequency speed. Supply frequency is having the rotational magnetic field, which is about the synchronous frequency. 2 pole 50 Hz. What is the synchronous speed? 2 pole 50 Hz. Synchronous speed कितना होगा आप देख लो, it will be 3000 rpm. 3000 by 120, 3000 by 60, how much it is equal to 50 rps, 50 revolution per second or 50 Hz, you can say. This is what Okay. So, suppose the slip is very small, slip is let us say 0.01, that means the rotor speed is how much? 50 into, so 3000 rpm into 3000 into 1 minus slip, that is the rotor speed, which is equal to 3000 into 0.99. So, that is about 2799, something like that. So, suddenly suppose the load is gone, the motor will accelerate. The motor accelerates because the load becomes less. It was the operating point, the load is thrown up, that means this becomes 0. So, there will be a lot of accelerating torque. So, this because of acceleration the rotor speed might exceed the synchronous speed because it is an inertial system. When the rotor speed increases the magnetic field speed, then what will happen? There will be speed will be negative. So, this negative speed called generating region, because omega s minus omega r, omega r is greater than omega s, so it becomes negative. So, this will become generating, that means the motor will feed power. So, that is called generating mode, but it will again come back and it will oscillate and stay at very small speed. So, then if the slip is between 0 and 1, it will be motor, but slip is greater than 1. What is greater than 1? I told slip is 1 here, but suddenly I reverse the phase sequence, A, B, C, I made ACB. A, B, C, but I made AC. So, motor which was rotating, the magnetic field rotating in this way, it starts rotating like this. Rotor is rotating like this, magnetic field rotates like this. The slip becomes more than 1. So, in that case, it is in the braking region. So, that is what it is saying, braking region. So, these are the 3 important regions: motoring, normal; generating when the overspeed, it is braking. Sometimes we use induction generators, we will not talk about it. In windmills, whenever there is a windmill, we using gear, we run induction generators, so that it can feed power back. So, this is one more topic which we will not discuss much, but that you can learn yourself. So, this is motoring, braking and generating. These are the 3 regions. So, if you look at them in the characteristic, it looks like this. In the braking region, it tapers down, slip more 1, it is same equation, this same equation, this equation. Put S negative, S more than 1, you will find this. This is a continuous operation. You see, this will become negative, that is braking region. And in this way, generating. Suppose there is a prime mover which moves the motor, which will be more than the supply frequency, it will start generating. That means you are feeding the 3 phase, but there is a prime mover, some wind or with some gears, we try to move the motor more than 50 Hz, it will keep on generating. So, this is generating region. Here the generator, the torque becomes negative, that means that they will be opposing from the other side. So, it is generating region. So, this is called the total operating characteristic of the induction motor. So, as you can see in the motoring region here, so there is a maximum torque. What is the condition for maximum torque? You have to differentiate this with respect to slip, because slip is varying. So, if you differentiate, you will get a condition. This is how. If you just divide, you will find this becomes the maximum torque region. You have to differentiate the torque and equate it to 0 to get the maximum torque, and this becomes the expression for maximum torque. That means, the position of the maximum torque depends upon this S max T, where the maximum torque occurs. It depends upon rotor resistance, also the starter equivalent resistance. If I change rotor resistance, this point will change, this point can change, this will go this way or that way. So, that is another way of speed control. If I can control the starter resistance also, it will slightly change. So, depending upon this, I can change the maximum torque region. So, this is called condition for maximum torque. For that, you have to do this one. In this case, you have to just differentiate this whole thing with respect to S and make it equal to 0. All right. The best thing is, what you can do is, you can multiply S in the denominator, multiply here, then you find out the minimum value. So, this you can do easily. So, this becomes R1 EQ square into S. So, you can do that, I can just do it for you. So, you just multiply S everywhere. So, this becomes, the denominator becomes what? So, here the denominator, if I multiply this S, because this is only varying with S. So, this denominator become REQ square into S plus R2 square by S plus 2R1 into R2, then it becomes S plus x1 x into x1 EQ plus x2 whole square. So, if you want to make it minimal, so this s into this will be equal to this. If you differentiate this with respect to dou s and make it 0. So, then you find the expression s. So, that is what is found here. So, this is the maximum torque equation, alright. So, I think this is what you have to do. Once you know this, so you move forward. So, you can find out the maximum torque or breakdown torque. That means, if you apply this Q, you replace by 3 phase. So, this breakdown torque depends upon the supply voltage and the rotor resistance, etc. If you cannot change this supply voltage square, if you keep on changing the voltage, the maximum torque will keep on changing. But you cannot apply voltage beyond certain value, because it will have insulation breakdown. So, the maximum torque is independent of rotor resistance, as you can see. So, it will it is not dependent upon rotor resistance, though the slip at which it is occurring is maximum. So, that means if you change the rotor resistance, what will happen to this maximum torque? This torque will change. So, it will keep on changing. That means, it will become like this, like this by different rotor resistance, but the torque maximum will not change. So, this is for changing. Rotor resistance will change. How can you change rotor resistance? You cannot change in squirrel cage, but you can change in slip ring. That means, the rotor is wound and there are wind is taken out of the slip ring induction motors, you can do that. So, you can change the resistance. Never found, so such kind of things are not required now. Now, we will solve this problem. I will give a half solution, then you can proceed and we will continue next class. So, this is one of the problems. What is the problem? Problem is a typical problem which you will face in the exam or maybe practically. A 3-phase star connected 460 volt line to line 20 kilowatt 50 Hz 6-pole induction motor has 20 kilowatt is when the motor power is mentioned, it is the developed power. How much power you are expecting the shaft? It is not the input power, it is the developed power. Remember, how much power is developed on the shaft. Here it is 2 HP written in that motor. So, that is the developed power on the shaft. Okay. So, then the resistance R1 stator is given, R2 the rotor resistance is given with respect to stator. Always remember, everything is given in place with respect to stator. X1 is the leakage, X2 is the leakage, all with respect to stator. Friction, core loss, everything to be constant 320 watts. Okay. And magnetizing reactance is 29. You see how less it is. Had it been transformer, it would have been 192. Because it is a induction motor, the magnetizing reactance is less. So, you can see. So, then what you have to do? So, this is the data which is supplied to you. Okay. 3-phase line to line voltage is specified, 50 Hz, everything is specified, 6-pole means the mechanical synchronous speed is omega e by 3, p by 2 na. So, omega e, so mechanical speed is less than the electrical synchronous speed. Okay. So, for a slip of 1.6%, that means slip is equal to 1.6, so 0.016, very less slip. Following quantities have to be calculated. What is the speed? What is the shaft output power, shaft torque, stator current, power factor, efficiency? All these things should be calculated. This will be all calculated from equivalent circuit. So, what is the equivalent circuit? This. We neglect the ED current branch. So, only this. This is the equivalent circuit. So, this is X1, this is R1, this is XM, this is X2, R2, then 1 minus S by S into R2. Okay, this is what. So, the supply voltage per phase is given V1, which is per phase is equal to 460 by root 3, right. So, these are all given, these values. So, from this S is also given. So, you have to calculate. 20 kilowatt is the nominal power, it is not the power specified. So, you can first calculate the current, slip you can calculate, slip is known. So, how does calculate the speed? So, mechanical maximum speed is equal to electrical speed by number of pole pairs, that is 3, p by 2. So, you can say the RPM is equal to electrical RPM by 3. What is electrical RPM? So it is 50 Hz. So 50 Hz will be 3000 by 3 will be 1000. So 1000 into 1 minus s. So what is the actual rotor speed? This is 1000 into 1 minus s. That is, you will find out. Then shaft output power, you can calculate the current, I2, etc. Shaft torque, stator line current, power factor, everything. Power factor is the phase angle between V1 and the I1 and cosine of the angle. So power factor. Then you can also do the same thing for the different slip 0.02 but using Thevenin's theorem. Then you find out the maximum torque, that expression. Then you will find out the starting torque. So these are the things which you have to do. So how to do it? So let's do step by step. I will go step by step. So step number 1 is, first of all, find out the phase voltage. That is 460 by root 3, 265.3. Then synchronous speed, 1000 RPM. This is synchronous mechanical speed. So this is 1000 RPM. Then synchronous speed is equal to this synchronous speed, mechanical. This is mechanical speed. This is mechanical speed, not the electrical speed. This is 2 pi ns by 60. So this by 60. This is all mechanical, not electrical. Electrical speed is this. Okay, 50 cycles per second. So then you calculate the impedances Z1, Zm, then Z2 is the rotor impedance R2 by S. So you compute this at this particular slip. Then parallel combination. So you do parallel of this and this. This is parallel with this, then series with this. So you do that. So parallel, then with series total you can do. This is done. J parallel. You can use calculator to do the complex calculations. Then you do this is the total. So divide, this is a current I1, total current. So this current, you have a phase angle. The angle is there. Voltage is angle 0. So you can find out the phase angle. So power factor will be phi is 10 inverse of this, 40.3 lagging. So cos phi is this, right? So this is the voltage, this is the current. This current has one real, one imaginary. So this is the real component, this is the imaginary component. So you can find out the power factor. This is lagging because the current will lag definitely, phi, this is negative, phi is negative. So power factor is found out, stator current is found out, speed is found out. So now what? Rotor load current. So rotor load current, how to find out? You find out E2. Once you find out E2, you can compute E2 by Z2 is the rotor load current. This is load current. Then air gap power 3 I2 square R2 by S, that is also computed. Rotor copper loss 3 I2 square R2, this is computed. Then electromechanical power developed, P mechanical, Q gap minus P rotor is this computed. It is not a big deal. So now come to next, shaft output torque. This is very important. A torque means mechanical power which is developed, it is again gone as friction and other losses which are called constant losses. So you can subtract this constant losses, P constant is equal to ED current can be also separated, friction and windage. Windage is because of viscosity. So both are subtracted, you get this is the power out from the shaft, this is shaft power which is available for the load. Then your mechanical speed is RPM which is this much radian. So multiply these two, this will get, divide. So this is the torque. This is Newton meter, this is the Newton meter, the unit is Newton meter. Then input power, so what is input power? 3 VI star, VI cos phi also it can do, 3 VI cos phi or 3 VI star. So this is the total power input and this is the total power output. So just divide, so efficiency is about 93%, which is less than, in transformer efficiency is 98%, but in motors because of rotation, because of magnetizing current etc. But still the motor efficiency is much higher and this can replace all the mechanical prime movers. Mechanical things are very lossy. If you bring a diesel generator to rotate something, diesel engine, it will be lossy. It will be 30%, 30% efficiency. But the electrical efficiency is 93% here. It is quite good efficiency. So let's go into the answers. So these are the answers. So I expect that you write all the answers in this way so that I can just check it and give you full marks. This is the answer. Then you go to the Thevenin's method, point S02. So you find out the equivalent voltage V Thevenin by that method, So in the Thevenin's equivalent, what are you going to do? You are going to get rid of this rotor circuit. That means you basically get rid of this rotor circuit. So, you just remove this rotor, you find out the equivalent here and the impedance. So, Thevenin's theorem. So, you do this. So, this is the equivalent voltage, open circuit voltage, and this is the equivalent Thevenin's impedance. So, then you put it in the circuit. So, this is now the simple circuit. That means this is the Thevenin's voltage, this is Thevenin's impedance, this is the rotor, this is the rotor circuit, this is rotor circuit, this is the whole thing is rotor circuit. So, this is Thevenin equivalent DTH, and this is Z rot, and this is VTH. So, VTH is there, ZTH is there, then this is the rotor circuit impedance JX2 plus. So, you know I2. So, you compute I2. It is very easy to compute I2. With the modern calculators, you can do complex manipulations. That is not a big deal. Okay. So, then what you do? You calculate the air gap power. You get air gap power. So, you get it 180 RPM. That you know. This is the new mechanical power. So, you can, this is Newton per meter. Please correct it, Newton per meter. So, mechanical power, then mechanical torque. So, everything is found out. Then maximum torque can be found out. So, how do I do maximum torque? You know, from the Thevenin's equivalent, you know this. You know this relationship we have already derived. So, you find out this S max T. So, which is this? Which is quite 7.53% is high. So, then what is the torque? Speed at this torque 1 minus S max T. So, this is the speed. So, torque becomes this. This is the pull out or maximum torque. So, again starting torque S equal to 1. So, if you put everything in the Thevenin's, this becomes the starting torque, Newton meter here, and this is the starting current. The full load current and starting current. This is the full load current, you can see, you calculate already 25.43, and this is the starting current about 4 times. Okay, this is starting current is about 4 times. In induction motor, sometimes it is 6 times to 4 times. So, that means the starting current, if you do, there will be lot of current will come in. So, therefore, if the current is too high, then you have to use some means, so that in starting you draw less current. So, those are sometimes called starting mechanisms. We will talk about it later. So, you can see, thank you very much for your attention. So, next class we will go into some testing, how to find out the parameters of induction motor. So, thank you.